Hey all, in today's lecture we are going to talk about measurement and significant digits. So let us start with the measurement first. So here the measurement, how it is defined. So measurement is basically the process of quantifying the attributes of an object or an event to compare it with other objects or events. It can be stated in another way also. So the another statement definition is measurement is a process of determining how large or small a physical quantity is as compared to the basic reference quantity of the same kind. We can understand it by simple examples. So here are some simple examples. So length of an rod is 10 centimeter. So here 10 is basically the length, 10 centimeter is length of the object, which is 10 times the centimeter, which is the smallest scale. Similarly, the mass of an object is 200 gram. So here the smallest unit of the measurement is gram, and the mass of the object is 200 times the smallest unit. This is 200 gram. So let us talk about significant digits. So significant digits are defined as every measurement. We know that every measurement involves errors. So thus, in a way, that indicates the precision of the measurement. So how it means that how precise the experiment is. Normally, the reported result of the measurement is a number that includes all digits in a number that are known and reliable plus the first digit that is uncertain. So there are two parts. One is the reliable certain digits, and another is unreliable or uncertain digit. So let us discuss it in detail. So the reliable digits plus the first uncertain digits are known as the significant digits or significant figures. Let us take an example to understand it or clarify it in more detail. So if we say that the period of oscillation of a simple pendulum is 1.62 seconds, then the digit 1 and 6 are reliable, and it means that they are certain, and the digit 2 is uncertain, and that these three digits 1, 6 and 2 reliable and uncertain digits combine to make significant digits. Clearly, reporting the result of measurement that includes more digits than the significant digits is superfluous and also misleading, since it would give wrong idea about the precision of measurement. Significant digits indicates the precision of measurement, which depends on the least count of the measuring instrument. Also, a choice of change of different units doesn't change the number of significant digits or figures in a measurement. We will understand this by a simple example. Simple example to understand the previous statement. The length 2.308 centimeter has 4 significant digits, 2308. But in the different units, the same value can be written as 0.02308 meter or 23.08 millimeter or 23080 micrometer. Now in all the cases, what you will see that the number of significant digits remain constant, that is 4. Now this shows that the location of decimal point is no consequence in determining the number of significant figures. Rules for determining significant digits. So let us discuss it. So all the non-zero digits are significant, number 1, and then number 2 is all the zeros between two non-zero digits are significant, no matter where the decimal point is, if at all. Now the third point is, if the number is less than 1, the zeros on the right of decimal point but to the left of the first non-zero digit are not significant. So let us take an example to understand this statement. So in 0.002308, the underlined zeros are not significant. So the only significant digits are 2, 3, 0, 8. The terminal or trailing zeros in a number without decimal points are not significant. Here is an example, like 123 meter is equivalent to 12300 centimeter or 12300 millimeter. Has three significant figures, the trailing zeros being not significant. So only significant digits are 1, 2, 3, whereas the other digits which arise because of the changing into the units are not significant. Now let us go to the another statement. So the trailing zeros in a number with a decimal point are significant. Like here, so if you have a decimal point and after that you have a trailing zero, that will be significant. Let us take an example to understand that. So the number 6.800 or 0.01300 have 4 significant digits each. Here the significant digits are in each case is 6800 or 1300. So there can be some confusion regarding trailing zeros. Suppose a length is reported to be 5.700 meter. It is evident that the zeros here are meant to convey the precision of measurement and are therefore significant. Now let us look at it into another way. Now let us change the unit. So 5.700 meter can be written as 570.0 centimeter or 5700 millimeter. Now, so according to rule number 4 discussed above, which says the number without decimal and trailing zeros have only significant digits as the numbers, not the zeros. So using that rule, what we do, what we deduce that it has only 2 significant digits, which is a wrong conclusion, as the change in unit doesn't make any impact on the number of significant digits. It means the number of significant digits remains constant, which is 4, as concluded above. To remove such ambiguities in determining the number of significant figures, we will define a new notation called scientific notation. Now how this notation is defined? So if you are taking any measurement, you can write it in scientific notation in terms of A cross 10 to the power B, where A lies between 1 to 10 and B, which can be positive or negative exponent of 10. Now B is also called order of magnitude, and for A less than or equals to 5, we will round off it to 1, and for A greater than or equals to 5 and less than or equals to 10, it will be rounded off to 10. So let us take a simple example to understand the scientific notations. So diameter of Earth is written in the scientific notation as 1.28 into the power 7 meter, where 10 to the power 7 is the order of magnitude. Now similarly, the diameter of hydrogen atom can be written as 1.06 into 10 to the power minus 10 meter. Here minus 10 is the order of the magnitude of diameter of hydrogen atom. Now what does it imply? So it implies that the diameter of the Earth is 17 orders of magnitude larger than the hydrogen atom. The power of 10 is irrelevant in the determination of significant figures, but base number in the scientific notation is significant. Let us then take an example to understand this fact. So 4.700 meter, which can be equivalently written as 4.700 into 10 to the power 2 centimeter, or 4.700 into 10 to the power 3 millimeter, or 4.700 into 10 to the power minus 3 kilometer. Now, in all the 4 representations, the number of significant digits remain constant, which is 4. So it means that the power, which is power of 10, which is different in different representation, has no relevance in the determination of significant digits. Now let us go to another important result. So it means that trailing zeros are always significant in scientific notations. So like if in base number, and but what about the zeros which are on the left side of decimal? So zeros on the left side of decimal are never significant, but the zeros on the right side of the are trailing right side of the number or trailing zeros are always significant. So another important rule in determining the significant digits is here. So multiplying or dividing factors which are neither rounded numbers nor numbers representing measured values are exact and have infinite number of significant figures. Let us take an example to understand that. So perimeter of a circle is equals to 2 pi r, where 2 is an exact number and it is a factor. So how it can be represented? 2 can be written as 2.0 or 2.00 or 2.00 etc. as required. Now let us go to the another rule, that is rules for arithmetic operation with significant digits. So in the arithmetic operation with the significant digit, the first rule is related to the multiplication and division. So let us state the rule and try to understand it. So in multiplication or division, the final result should retain as many significant figures as there are in the original number, with the least significant figures. Let us take an example to understand this multiplication and division. So density is defined as the mass divided by the volume. So let us take the mass of the substance is 4.237 gram and the volume is 2.51 centimeter cube. So here in the mass term you have 4 significant digits and 3 after the decimal, and whereas in the volume you have 3 significant digits and 2 after the decimal. So in the division the number of significant digits will be 1.69. Basically there will be 3 significant digits because the number of significant digits in the division are only 3 and 2 after the decimal places according to the rule described above. Now let us go to the addition or subtraction. So in addition or subtraction, the final result should retain as many decimal places as there are in the number with least decimal places. Now let us try to understand it. So you have a simple example like you 436.32 gram plus 227.2 gram plus 0.301 gram and is equals to 663.821 gram. Now how we can round off it as according to the rule. So the least significant measurement is the second one, where only one digit is there after the decimal. So in the final result we will keep only the one digit after this decimal. So the final result after the addition will be 663.8 gram. Rounding of the uncertain digits. So here are the rules for that. So the first rule is the proceeding digit is raised by 1 if the insignificant digit is, to be dropped is more than 5 and is left unchanged if the letter is less than 5. And the rule second is if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. So here is an example to understand this. 2.745 can be written equivalently as 2.74 as the preceding digit is even, 4, which is even, and in 2.735 it can be written equivalently as 2.74 as the preceding digit is odd. So it is raised by 1 and it converts to 2.74. So let us take a simple example of this rule of rounding of the uncertain digits. For a cube of size 7.203 meter, determine surface area and volume in significant digits. So, you know that the surface area of a cube is defined as 6 times side square. So it is just put this value 7.203, which is the length of the side, and when you multiply and calculate it, what you exactly will find that it is 311.299254 meters square. Now, when you will round off the digits, you will find that you have to round off in the same keeping the same number of significant digits as there are in the side. So the total number of significant digits must be 4. So following that rule, you have to keep it up to the first order. So it will be 311.3 meters square. Similarly, when we are going to volume, which is equals to side cube, and where side is A here, so it will give you 373.71474 meter cube, which can be equivalently written as 373.7 meter cube in the round of digits. So rules for determining the uncertainty in results of arithmetic calculations. So let us discuss the first rule. So in multiplication or division, maximum percentage error will sum up. So let's take an example to understand this statement. So area of a rectangle is defined as the length multiplied by the breadth. So if L is defined as, or length is defined as 16.2 plus minus 0.1, and breadth B is defined as 10.1 plus minus 0.1. Then the area will be defined as L cross B, so it is equals to 163.62 centimeters square plus 1.6%, which is equals to 163.62 plus minus 2.6 centimeters square, which is nearly equals to 163 plus minus 3 centimeters square. Now, how did we achieve this formula? Just by using the method for calculating the maximum error. So you take area as L into B and take the natural log of on both sides, and then take differential of it, which you will find that dA by A equals to dL by L plus dB by D, and for the maximum percentage error you will simply multiply by 100 on both sides. So what you will observe that this error, where dL represents the least count of the measurement for the length, and dB represents the least count for the measurement of breadth, multiplied by the total length, total width measured, you will simply get this percentage error as 1.6, and then when you multiply with this number A, you will achieve 2.6 centimeters square as the error, which in the round off is obviously achieved as 163 plus 3 centimeters square. So, if a set of experimental data is specified to insignificant figures, a result obtained by combining the data will also be valid to insignificant figures. Now, the third point is the relative error of a value of number is specified to significant figures depends not only on n but also on the number itself. Let us take a simple example to understand what we said in the last statement. So accuracy in measurement of mass m1, which is equals to 1.02 gram, is plus minus 0.01 gram. Similarly, accuracy in measurement of mass m2, which is equals to 9.89 gram, is same, which is equals to 0.01 gram. Now let us calculate the relative error in both the masses. So for the first mass, it is plus minus 0.01 divided by 1.02 into 100, which gives you plus minus 1%. Similarly, when you go to the M2, here you will get plus minus 0.1%. So rule 4 is, so intermediate results in a multi-step computation should be calculated to one more significant figure in every measurement than the number of digits in the least precise measurement. So let us take an example to understand the statement. So reciprocal of a number 9.58 is equals to 0.104 with same number of significant digits. Now, if you again take the reciprocal of this number 0.104, we will get a different number, which is 9.62. Now, so what we need to do to get the same number which we started with. So let us increase this number of significant digits by one more in the reciprocal number. So now take it as 0.1044. So here the last one is the extra digit. Now when you again take the reciprocal of this number, which is 0.1044 with one extra number, you will exactly find the same number which you started with. So